Everyone can see the title slide for this presentation. Thanks everyone for being here, and thanks to the organizers for having me. I'm kind of new to this community, and it's an honor to get to present. So today I'm going to talk a little bit about this kind of approach to updating multivariate or doing a multivariate update for state quantities that are constrained by summation, which is some work that I've been doing with Jeff Anderson at NCAR. I'm going to get a little bit to what I mean exactly by performing multivariate updates when your state quantities are constrained by their sum in just a second. But first, I want to establish that we're going to operate under the assumption of a two-step ensemble data assimilation framework for the rest of this talk. So if you're unfamiliar, this is an approach that splits the data assimilation update cycle into first an observation space step, in which the ensemble estimates of an observed quantity, shown in this schematic as blue triangles, are updated via a comparison to the observation, which is shown as a purple triangle. That is then followed by a state space update, in which each quantity in the model state is updated via a linear regression of the observation increments shown in the green arrows that were calculated in the first step. So hopefully being all on the same page that this is the framework that we're going to use, we're motivated to use it because it allows for a pretty tidy formulation of the ensemble DA problem, and it allows us to examine in detail features that are related to both the observation updates and the state updates independently. So as to the problem that we're interested in, our motivation is basically to update the estimate of a model quantity X given some observation Y naught. The basic constraints on this problem are that Y naught is a real world observation of the quantity X, and X is a diagnostic variable that is calculated as some function of underlying state variables. So far, there's nothing that's particularly unique about this set of constraints when it comes to a DA problem, but the thing that we're really interested in involves this additional set of more particular constraints, namely that Y naught and X represent a quantity that is physically bounded to be non-negative and less than some total value S, which for most of this talk is going to be 1. We're also going to say that X is specifically defined to be the sum of a number of subcategories X sub n, and each of those subcategories, which are state variables, are also bounded between 0 and the total sum S. So these additional constraints define a system that is a challenge for standard DA approaches, which typically don't like bounded non-Gaussian behavior. And we can illustrate some of these challenges with a couple of simple examples. So our first is going to be an example in which we consider an observed variable for which the majority of the mass of that observed variable is held within a single unobserved subcategory. And I'm going to illustrate that with this schematic where the ensemble prior estimates of the observed variable are shown on the x-axis as blue dots, and the prior estimates in the ensemble for the unobserved subcategory variable are shown on the y-axis in blue dots. The updated posterior ensemble estimates are shown in teal on the x-axis as a result of assimilating some observation represented here in the purple X. So in this example, the relationship between the observed and the unobserved subcategory variable is extremely straightforward in that it is a perfect one-to-one line and it's very well behaved. And as a result, when we project the updated observed ensemble onto this one-to-one relationship in order to obtain estimates for the unobserved variable, we obtain a posterior ensemble for that unobserved variable that mirrors pretty much exactly the observed ensemble. In this idealized example, there are really no issues with standard state space regression DA approaches. However, it doesn't take very much for us to move off of this pretty perfect example. And one example is if we start to consider multiple subcategories contributing to an observed variable. So if we consider this multi-category case in which only some of the mass in the observed variable belongs to an unobserved subcategory, then we can see that we shift our linear relationship between the observed and unobserved variables away from one-to-one. And additionally, our ensemble members are not constrained to perfectly lie on that linear relationship. And so in the face of, for example, a particularly large observation increment where we have a large difference between the observed value and the prior ensemble mean, when we shift these ensemble members along this linear relationship, we can wind up with posterior ensemble members that have estimates for the unobserved subcategory variable that violate the physical bounds we imposed earlier. So you'll note here I've highlighted some posterior ensemble members that do not violate the bounds of the observed variable, but do wind up with negative estimates of this unobserved subcategory. There are also versions of this problem in which you update multiple subcategories and wind up with sums across those subcategories that violate the upper bounds on the observed variable, which is harder to illustrate with this kind of schematic, so I'm not showing it directly. But both of these kinds of things are non-physical and can lead to errors in our forecast model if they are returned to the model. So there are real issues with this in geophysical models, and one very good example of a geophysical model that captures both of these problems is sea ice. So here I'm illustrating a common sea ice model, IcePack, which represents a sea ice variables like sea ice area, thickness, and snow depth within a single grid cell. And when we represent sea ice area in particular on this kind of grid cell, it's typically represented as a sea ice concentration, which is a fractional ice coverage that is bounded between 0, no ice cover in the grid cell, and 1, which is total ice cover in the grid cell. Ice thickness and snow depth are averages in a grid cell and constrained to be non-negative. In practice, IcePack improves the accuracy of its estimates for these variables by representing them on what's known as an ice thickness distribution, which is simply a subcategorization of ice in the grid cell based on a number of ice thickness categories. Typically, in most applications of the model, that number is 5. Sea ice concentration is then subdivided into an areal fraction per category, and ice thickness and snow depth are represented as volumes per category. The distribution of total sea ice concentration or thickness across categories depends on the kind of sea ice condition that we're representing at the grid cell in question. So for example, I've pulled out a couple different representative sea ice regimes that you might see in a larger geophysical model, where on the top, we're talking about seasonal ice, which in the black line in total sea ice concentration oscillates over the course of the year from total sea ice coverage to next to no sea ice coverage. And for which the kind of fractional subdivision of sea ice concentration across the area subcategories shown in the colored lines varies pretty widely throughout the year. We can also look at a pack ice environment, which is typically thicker and has sea ice concentration that stays near total coverage throughout the entire year, and has a much more even distribution of sea ice concentration across its underlying subcategories. Finally, we'll consider a first-year ice environment, which melts out completely each summer and regrows each winter, and therefore has most of its sea ice concentration held within the first and thinnest ice category. So the sea ice problem, hopefully, at this point, you can understand that it captures a lot of different combinations of subcategories contributing to an aggregate total sum variable, and gives us a playground in which to kind of explore the different challenges that this setup presents for us. There have been a couple different swings at this regression problem for updating subcategories based on an observed aggregate. And the first of those is probit regression in the quantile conserving ensemble filtering framework, which seeks to avoid the kind of bounds violations that we illustrated with this figure earlier, by transforming both the observed variable, in this case sea ice concentration, and the unobserved variable, these area subcategories, from a bounded space into an unbounded space using a probit function. The regression then occurs in the unbounded space and afterwards is transformed back into the original bounded variables, which produces a different update to the posterior unobserved category variables that does not have the bounds violations that we highlighted earlier. So that's a really nice feature, but one kind of alarm bell about this method is that we can see that there can arise kind of a suspicious relationship between the mass in a subcategory and the total mass in the observed quantity. So I've highlighted here some posterior members in the red circle for which the subcategory area fraction in these members sits around 0.8, but for which the total observed sea ice concentration summed up across all categories sits at no more than 0.3 in the largest ensemble member. That should definitely ring some alarm bells in a subcategory that contributes to a total has more than twice as much mass as the total itself. And in fact, when this occurs, the subcategory results have to be post-processed in order for the model to make a forecast in time. And the frequency of this post-processing can be quite high, which is illustrated by this figure. So here I'm showing the post-processing requirements in a change to total sea ice concentration that is required to satisfy physical bounds on both the unbounded and bounded quantities over the course of a 365-day assimilation experiment in a seasonal ice regime. So the gray lines illustrate the post-processing requirements for every individual ensemble member, and the black line represents the post-processing requirements in the ensemble mean, where I've overlaid them on a dashed line that represents the annual cycle of the seasonal sea ice concentration, so that you can see that a lot of this post-processing occurs when the categories have to sum up to a total sea ice concentration of 1. And since this kind of post-processing is undesirable because it tends to degrade the accuracy of our analysis, and it occurs quite frequently in this kind of ice environment, we want to consider another approach that may not require post-processing. Another that has been put out there is rescaled disaggregation, which is a much simpler approach, mainly because it avoids regression entirely, and simply divides the observation increment shown here in blue for something like sea ice concentration proportionally amongst the subcategories by scaling the increment according to the prior fraction of the total mass that belongs to each subcategory in the prior ensemble. The pros to this are that it's simple to implement and it's pretty intuitive. It's also been shown in some applications for total terrestrial water storage to avoid strong model responses or shocks to the kinds of updates that you would get if you were not maintaining these kind of relative proportions among the categories. But the cons are that it requires the observed quantity in the subcategories to have a pretty direct summation relationship, and it does not use ensemble statistics to disperse updates throughout the model. So in light of these drawbacks, we're proposing an alternative method, which we're calling normalized regression, and which does not violate physical bounds, but does utilize the ensemble to make multivariate state updates. So to outline this pretty briefly for you, we're first going to establish that the sum of all the prior subcategory variables and the sum of all the analysis subcategory variables needs to add up to 1. Secondly, we're going to introduce the use of a placeholder variable z, which represents a relative fractional amount between 0 and 1, and is defined such that the sum of x's and the sum of z's across the subcategories are related by some scalar alpha. When we start in the prior, physically, the sum of z's and the sum of x's is going to be 1, so the alpha in the prior is also going to be 1. We then perform updates to the relative fractional amount z using probit regression, which maintains the physical bounds on each subcategory between 0 and 1, and produce a set of analysis values for z. The alpha that relates the sum of x and the sum of z in the analysis is equal to simply the sum of the z values, since we already established that the sum of the analysis x's is going to be 1. And the alpha can then be used as a normalization factor to recover the analysis state values x. So this method is on its face actually pretty simple, and it's just effectively a blend of regression with a form of rescaling, which allows us to use the benefits of both methods without the drawbacks of either. To test it, we've implemented it in a series of 3 sea ice experiments, each focused on a different type of sea ice condition that we outlined earlier. And in each experiment, we assimilated observations for 365 independent data assimilation cycles and compared these different methods for updating the state categories. So in the first experiment, we assimilate sea ice concentration observations to update the sea ice area subcategories in an apples to apples comparison. And we do this in seasonal ice, where you'll remember the mass distribution of total sea ice concentration across the area categories varies a lot throughout the year. In these plots, the red line represents the target true state, the black line represents the prior ensemble mean, and the orange line represents the posterior ensemble mean when we used our normalized regression method to update the state. The blue line presents a comparison to a posterior mean when rescaled disaggregation, was used to update the state, excuse me. And the adjustment to the total sea ice concentration is shown on the top left, with the updates to each of the individual subcategories progressing from left to right. So we'll first note that rescaled disaggregation seems to slightly outperform our new method in terms of total sea ice concentration in this region that I've highlighted in black, where the prior mean and the true state differ pretty significantly, largely because it outperforms the new method in the first subcategory. Though we'll note that both of these methods do make notable improvements to the model state relative to the prior. However, a knock against rescaled disaggregation in this case is that because it relies on the relative amount of mass from the observed variable that's in each subcategory from the prior ensemble, it's sensitive to timing differences in this particular period in the fall, where we rapidly go from very little sea ice to total sea ice coverage in this grid cell. And so the rescaled disaggregation is making updates based on the timing of that change in the prior, and therefore leads to some pretty wonky updates compared to the posterior and the true state. In the second experiment, we compared our new method to disaggregation in first-year ice, where the vast majority of the ice is in just one thin category. And here we note that normalized regression outperforms disaggregation in all subcategories, though they perform similarly if you look at total sea ice concentration in the upper left. Again, this outperformance of disaggregation by normalized regression is because of the reliance of the disaggregation on information from the prior, which leads to this kind of erroneous creation of ice in the posterior estimates for low mass categories, because disaggregation can't account for how the proportion of each category will shift from time step to time step. The third version of this experiment tested these methods in the pack ice environment, where the subdivision of total sea ice concentration is relatively even across categories. And you'll notice pretty immediately, it should be pretty obvious, that neither method adjusts total sea ice concentration or the subcategories. But this is largely due to the fact that ensemble spread and sea ice concentration in the upper left is so tight in this environment, because it's nearly always ice covered, that there's no notable sea ice concentration increment from the observation space update to either disaggregate or regress onto any of the subcategories. However, you'll note that in the individual category subplots, there is spread in the subcategories. And so in theory, we might be able to use information from other observations of the CI system to get around this limitation. When we assimilate observations of sea ice thickness, for example, and do a kind of apples to oranges comparison, we can find that we shift the subcategory estimates away from the prior ensemble mean, which is a step forward. And we note that in this case, disaggregation degrades estimates of the subcategories. The blue line shifts away from the true state and violates the upper bound on total sea ice concentration in the upper left pretty consistently, which is largely because the sea ice thickness observation increment has no knowledge of the upper bound on sea ice concentration. We also, oh gosh, I jumped quite a few slides, didn't I? Okay, great. We're also going to note that normalized regression here avoids these problems and allows for positive adjustments to the subcategories, as well as avoiding any violation of total sea ice concentration bounds in the upper left, even when we assimilate an observation type that is not directly related to our subcategories. So to summarize, we've tested a new normalized regression approach that succeeds in updating categorized state variables without violating physical bounds in any step of the DA cycle. And we find that it increases accuracy and applicability compared to existing methods. We also note that it avoids small but pretty meaningful errors that can crash our forecast model, which is really helpful in a practical implementation. And we find that normalized regression allows us to improve estimates of subcategories when assimilating observations that are not sums of those subcategories, which gives us some flexibility in how we go about correcting the underlying state of the model. Our next steps involve exploring the impact of normalized regression in online experiments where each DA cycle is actually linked by a forecast step and not independent from every other DA cycle, and then verifying this performance in larger models and other geophysical variables. With that, I will say thank you, and I'm happy to take any questions.
Thank you, Molly. That talk was excellent. So on the Yopad, to start with, we have a comment and a question from Peter Jan van Leeuwen. So I'll read from the Yopad. Peter Jan says, one, if we could use a particle or another fully nonlinear DA method, this issue of unphysical updates would not appear, I think. As an example, each particle in a particle filter will fulfill the conditions in the prior, so also in the posterior. And then a question following on that, Peter Jan asks, a linear DA method should conserve the linear summation constraint, ignoring inflation and localization. So is the issue the additional positivity constraints?
First, I want to acknowledge it's a great point by Peter Jan that using a nonlinear DA method should help with some of these things. There are still limitations on some of the nonlinear DA methods that you'll use, particularly when you're thinking about the fact that for each subcategory, we can only place kind of physical constraints on that subcategory to be 0 and 1. And so when we add them up, there's no guarantee that they then meet the physical constraints on the sum that is also 0 to 1. And that's an issue that we were running into when using a nonlinear formulation of the quantile conserving ensemble filtering framework. I've not run it with particle filters, so I'm not entirely sure how it would play out in that scenario, but I can imagine that you might still run into some of the bounds violations as a result of summation issues that we're encountering with other nonlinear filters. The linear DA method conserving the linear summation constraint. In theory, yes, but in practical application, because we're treating each of the subcategories as an independent state variable, they're not really acting in concert with one another. And so the linear relationships that are being calculated between the observed variable and the each unobserved state category variable are really only aware of those two quantities, right? And so there's no actual translation across the categories that says that the updates that you get for each individual subcategory will preserve the summation in the end, as it would turn out in our practical application for CI. So I hope that helps a little bit. Peter, if you would like to talk a little bit more about these constraints, I'm happy to do that online, but I think I'm going to leave it there for the direct question.
Thank you, Molly. And Hristo Kapilski asks, I would like to understand the connection between your method and the mixed Dirichlet approach from Bowden and Grooms in 2025, which deals with a similar problem of updating state variables that sum to 1.
Yes, yeah. Thank you, Hristo, actually, for bringing this up. I think Kate is here today, actually, but a lot of this work has evolved kind of in concert with the stuff that Kate and Ian have been thinking about. I'm going to say that I think from a mathematical perspective, the approach that Kate and Ian are pursuing is probably more complete in that it is thinking about how to do transport on a simplex. So you're thinking about the constraints a little bit more holistically, but their method is a little more involved to implement. And so we were kind of motivated by coming up with a solution that would be easy to implement within a DA framework that is already set up and running. So there are definitely overlaps between the two. I would really recommend checking out their work if you're not familiar with it. But we were really motivated by a more simple implementation that addressed the basic constraints of not violating bounds in any step of the DA process and the sums being consistent with the observed variable.